Hi everyone, thanks for watching our good project. Our project is mainly talking about RSA and ECC's practical application. First of all, let me introduce some basic and historical information about RSA. RSA is a public key crypto system that is widely used for secure data transmission. It's also one of the oldest. And here you may be curious about the name of RSA. It doesn't have some special meaning. It's just a surname of its inventors, Ron Rivest, Eddie Schmier, and Leonard Edelman. And they publicly described the algorithm in 1977 and proposed in 1978 in MIT. And RSA is the first theoretically most successful public key crypto system. Its security is based on the ALU theorem in number theory and the following thesis in computational complexity theory. It's easy to calculate the product of two large prime numbers, but it's very difficult to decompose the product of two large prime numbers and find their prime factors. So just to speak simply, it's just used to deal with factoring problem. And let's then talking about the algorithm of the RSA. We need to firstly create two prime numbers P and Q and let them then length k divide 2 in order to make sure the prime number will not be too long. And then we can count the public k. And for the next step, we can use the two formula to get the ke and kd, which is used to encrypt and decrypt. This two formula is sufficient and necessary to each other. And then we can use a loop function to get prime number, as we have mentioned above. And by the end of these steps, we could have public key, encryption key, and decryption key. And so then we can get the plain text and the ciphertext. So the whole algorithm is like this. Here's the simple flowchart to show the whole step clearly. We need to first of all read the file, and if this step successful, we can then call function to encrypt or decrypt, and then we can just write the encrypted file out or the decrypted file out. And here's just some small conclusion for the RSA. It just use random small prime numbers to get large prime numbers and generate public and private keys. So let's move on to the code part.
Hi, this is John Hao. So the first thing we need to do, just like we introduced above, we have to generate some large prime numbers from some random small numbers here. So the first thing I will introduce to you is to a function in our code, which is the create prime number function here. One thing we need to mention here is that we have to make sure that the product of two prime number won't be too large here because it will make our calculation too large and will take a lot of time here. So we hate the half of a key length here. So what this function does is to while true, make it into a loop here. So the first thing we need to make sure that it shouldn't be even, right? So if it's not even, it is an odd number, then we need to test it. What we write here is a middle Rabin test function here. It is basically a function we wrote in our code. I won't introduce. I won't show you the code here, but it is a primality test. It is an algorithm which determines whether a given number is likely to be prime here. So we will pass in this prime number that we generated here. We test it like 10 times. It will improve our accuracy to make sure that it will be a prime number for sure. And it will pass and go for another round of tests until the 10 rounds is passed. If it's not, if it fails the test, then it is not a prime number, right? So it will go here again and generate a new random number here. So eventually it will give us a prime number here. So after generating the large prime number, it will be easy now. So the next function here is to generate the keys, which will generate the E and a D, which is the public key and a private key here. Just like what we mentioned above, the key length shouldn't be too long, so it is a half of our key length here. So it is divided by 2. And also we will calculate the Euler function value here, which is the product of a P and Q here. And the function that we produce the public key and private key here, we will show you in our next page here. So this function is what we used to produce our public key here. It is we will generate the E based on our Euler value here. So we have to make sure that the greatest common divisor here will be equal to 1. And after this loop, we will return our E here. And the private key here, we have to make what we does here is to, based on our public key, we have to match our only D here, which is our private key here. So after getting our public key and private key, it is now we need to run this code, and what we'll do here is show you our run result here. What we did here is put our members 3 haiku text here. As you can see, it is showing here, totaling 9 lines here. And it will give us, at the beginning of our code, it will give us 3 options here: the encrypt and decrypt and encrypt. As you can see, we choose one here, which is to encrypt. We're taking our 3 haiku texts here, and it will generate our D and E here, the public key and private key, and our N, which is the product of a P and Q here. And after decrypt, it will show us the text here. As you can see, we can now read it, right? It is encrypted. And we will show you the result of the decryption, which, as you can see, we can choose to here and decrypt. And this is the public key. This is the private key that we recorded during our last process. As you can see here, we keep this key and we can use it in our decryption. So it says decryption done, and we can successfully see our haiku texts. So before we move forward to ECC, let's have a recall what elliptic curve means. So we have our definition here, and elliptic curve in mathematics, an elliptic curve is a smooth projective algebraic curve of a genus 1 on which there's a specified point O. So we have our equation here, but let's have a look here. We also have to satisfy this equation here. This restriction is to ensure that the curve does not contain singularities. And this equation also has a name called Weierstrass normal form here. The set A and B has a collection of points representing an elliptic curve. We need to solve for the A and B. How we solve it? So for each x, we calculate x to the cube plus ax plus b mod p. So we check the value here. If the value in step 1 has a square root after mod p, we calculate y squared mod p. So if there isn't a square root, so there isn't a corresponding point on the curve. If there does exist a square root, we solve these two square roots. Now let's make an example. We solve for e to the 11 and 1 and 6. So what we have here is that a equals to 1 and b equals to 6. So we get the curve equation here. Let's see, we plus 1x and 6 here. So let's code this and have a greater understanding of this equation here. So there we have the code. We code a function here that show points. We have our p, which is a range, and a and b. We listed our equation here and show the and printed out their points. And the result is here. We can see that all the points, they are both for the x and the y, they're both less or equal to 11. So this is the right result here.
Okay, now we talk about the group theory on elliptic curves. So we can define a group on elliptic curves by these 4 points. First, the elements in the group are points on the elliptic curves. Second, the identify elements is the point 0 at infinity. Third, the opposite number p is the point on the other side of the symmetry about the x-axis. Fourth, the addition rules is defined as follows. Take 3 points on a straight line P, Q, R, and their sum is equal to 0. It means P plus Q plus R equal to 0. Okay, now we talk about the operation rules of elliptic curves. This is a picture from the professor's slide. It describes the following relationship between the straight line and curve. Since the point side of the elliptic curve belongs to an abelian group, we can write P plus Q plus R equal to 0 as P plus Q equal to minus R. When we draw a straight line through P and Q, this line will intersect the elliptic curve at the third point R, which means that the 3 points P, Q, and R are on the same straight line. At the same time, the opposite point is minus R. When 2 points overlap, the tangent line of the elliptic curve at point P, the intersection point of the elliptic curve, and the point at which the intersection point is symmetric about the x-axis are defined as P plus P, which 2P. For the third situation, the symmetrical position of P with respect to the x-axis, which is the minus P. So it is the inversion operation of the sign of the elliptic curve. If P plus P equal to 0, and the line passing P is parallel to the y-axis, it can be considered that the line and the elliptic curve intersect at the infinity. So therefore, we set point J is called the base point, which is on the elliptic curve, and the P is the private key. K is the public key, which equal to P times G. And when we get the point G, we can easily to calculate 2G, 3G, 4G. That means when the G point is given, P is known, and it's not difficult to find the PG point, which the public key K. On the contrary, if only know the PG and the K, it is very difficult to find the P. So this is the mathematical principle behind the ECC algorithm. So now we can see how to get the public key equal to PG is equal to G plus G plus G plus G is totally P times G. So for example, when we set the P equal to 151, it equal to 100101111 in binary. So the 151 can equal to 1 times 2 power 7 plus 0 times 2 power 6 plus 0 times 2 power 5 plus 2 square. 151 times G is equal to 2 power 7 G plus 2 power 4 G plus 2 power 2 G plus 2 power 1 G plus 1 G. And here is the code how we calculate the public key. So now we talk about the process of the encryption. How we encryption by use the ECC. We got two people, Alice and Bob. First, Alice select elliptic curve E and take a point as the elliptic curve as the base point G, and they calculate the order of the base point G is N. Alice choose a private key P and generates a public key K equal to P times G. Then Alice sends the public key, sends the elliptic curve E. Order of the base point G is N to the Bob. Bob received the message and he encoded the plaintext to be transmitted to a point M and generate a random integer R, which are smaller than N. And then Bob calculates the points C1 equal to M plus RK, R times K, and C2 equal to R times G. Then Bob passed the C1 and C2 to the Alice. After receiving the information, Alice calculates the C1 minus K C2, and the result should be the point M. So when we run our program, suppose the input elliptic curve parameter A, B, P. For example, we can set A equal to 7, B equal to 11, P equal to 29, and it will be build a elliptic curve showing on the graph. So the point 1 on the graph can build an elliptic curve. So all of the point is on the elliptic curve. So we choose one as our base point G. And we got the test result. When we said the G is 2.2 and the N is 23, we choose the private key 22, which is smaller than 23, and we can calculate the public key. Now we test, can we encrypt and decrypt the plaintext? So we successful to encrypt and decrypt the message. So here's some code. We how to calculate the P and Q, P plus Q, and we how to calculate the order, means the base order, the N. Then we do the test. We can see when we use the same time, the key length RSA is way larger than the key length of the ECC. So that concludes the RSA algorithm. Increasing the number of the digits of n equal to p times q will greatly improve the security of the RSA crypto system. but the amount of the calculation increased exponentially, making it more difficult to implement and less practical, to some extent to limit the scope of the application. In the RC algorithm, the calculation is very time-consuming, so we believe that the actual application process, the complexity of the calculation should be reduced under the premise of the centering security. So we can see the ECC and the RC, the difference. For the 160-bit ECC has the same security string as the 1024-bit RC, and the ECC has the faster processing. In terms of the processing speed of private key, ECC is much faster than RSA. ECC requests a lower bandwidth requirement and less storage space. The key sets of system parameters of ECC are much smaller than RSA, but only one question. The design of ECC is very difficult and the implementation is complicated. And alright, thank you so much. Thank you all. Thanks for watching our project. That's all.